-4. Wait a minute, does that look fishy? It should. Okay, it says non-real. Remember we said for our rules for logs, x has to be positive. Okay, so we can't find the log of a negative number. Okay, so we'll just say that this is undefined. Okay, it's only defined for positive x values. Okay, graphs. Here's a to the x, and we looked at exponential functions. A to the x graphs looked kind of like this. Okay, depending on what your base is, it varies a little bit. They have an asymptote at y = 0. The domain is all real, and the range is all positive y values, so, and not including 0. So soft bracket at 0 to infinity. So if we're looking at the inverse of that, we can reflect this in the line y = x. Okay, so I'm just going to imagine, obviously I'm not imagining, I'm drawing, sorry. If I sketch in the line y = x, okay, what's going to happen to that horizontal asymptote? It's going to become a vertical asymptote at x = 0, and our function is still going to go along the asymptote. This one shoots off to infinity this way. It's going to come along this vertical asymptote and shoot off to infinity this way. So it looks something like that. So now our asymptote is vertical at x = 0. The domain is no longer all real because we can only take the log of positive numbers, so this should make sense. This is only going to be from 0 to infinity. But the range is all real. You can get any kind of number out. So the domain of a logarithmic function of log base a, you have to make sure that your x values are positive. And that's the reason I'm rewriting it is because when we go to find the domain of a log function, that's what we're going to worry about. Whatever you're taking the log of has to be positive. Okay. The graph of every logarithmic function passes through 3 points. It'll pass through a, 1, so whatever that a value is. It'll pass through 1, 0, and it'll pass through 1 over a, -1. And these are really only the only points I'm going to worry about for graphing these. I'm going to go ahead and pause there. See you in the next video. Okay, so we're going to find the domain of some logarithmic functions, and this is the rule up here that we're going to use. This x has to be greater than 0. So whatever you're taking the log of has to be positive. Okay, we don't care about the base. I don't care anything else that's happening outside of the log. Whatever you're taking the log of, in this case 4 minus x, has to be positive. Okay, I'm just going to add x to both sides. X has to be less than 4. So if I write that in interval notation, that would be everything up to 4 exclusive. Okay, for b, whatever's in the parentheses, whatever you're taking the log of, has to be positive. Add 5 and multiply by 2. X has to be greater than 10, so this would go from 10 to infinity. Okay, for c, if there's no parentheses, this -4 is not inside the log, so it's just the x squared. It's inside the log, so x squared has to be positive. And this is a quadratic inequality, so this is where you want to use the number line. The only 0 of that would be 0. And let's see, if I pick something that's negative, is a negative squared greater than 0? Yes. Okay, it comes out to be positive. And is a positive squared greater than 0? Yeah, all of that works too. It's the only thing that doesn't work here. Okay, 0 itself. Okay, I need it to be strictly greater than, and 0 squared is exactly 0. So that is the only thing I need to exclude from my domain. X cannot be 0 here. So if I'll put it, I guess I could just put it like that, all real except for 0. Or you know the other versions, hopefully, of that by now. And last one, this is a rational one, so this is another one where I would want to use a number line. This one, x divided by x minus 1, has to be positive. Okay, so when I put things on a number line for rational functions, I need any zeros, okay, which means zeros of the numerator, and 0 will make this numerator 0, or zeros of the denominator. In this case, 1 would make the denominator 0, okay, because those are places where this function could change sign. It could go from positive to negative or negative to positive, so I need to test these things. If I test something to the left of 0, okay, this would be a negative over a negative, which would be positive. If I test something between 0 and 1, this would be a positive over a negative, which would be negative. And if I test something to the right of 1, this would be a positive over a positive. Okay, so there are two intervals that I want, two places where this thing is greater than 0, and that's going to happen to the left of 0, and that's also going to happen to the right of 1. So the two intervals I want negative infinity to 0, unioned with 1 to infinity. Okay. We are going to graph a couple of these just by transformations. These are going to be quick graphs, and then we'll graph a couple more with points and actually make those more accurate. So this one, log base a of x minus 4 plus 2, we know what the typical log function looks like. Okay, it's got a vertical asymptote and then comes off like this. This one has been shifted where? Okay, it's been shifted to the right 4 and up 2. Well, shifting to the right is going to change our asymptote. That's going to shift it, let's call this 4 over here. But shifting up or down will not change the asymptote, but it will, instead of crossing like just to the right of the asymptote, normally we'd cross the x-axis, that would shift up 2. So it would, kind of that bend where it starts to go off to infinity would shift up a little bit. That was my husband busting in. Sorry for the noise, but we can't blame him. He brought me a sandwich. So, pause for now. I'll be back. Okay, for B, this negative x is actually going to flip us in the y-axis because it's inside of the function, and then we're going to shift it up 4. Okay, so again, our asymptote doesn't change if it's shifted up or down because it's a vertical line, so it'll be in the same place. But the negative x is going to flip us to the other side, okay, and then shift up 4. So remember that point I kind of talked about, kind of where it goes from being kind of straighter to curving off. On this one, it's going to happen up 4. So it's going to stay next to the asymptote for a little bit longer, and then right around wherever x equals 4 is, we would start to veer off and to the left this time because of the negative x. Okay, for these next ones, we are going to get a little bit more specific, but we're just going to use those points that I talked about in the table a little bit ago, these three. A, 1, 1, 0, and 1 over a, negative 1. So if the base is 5, okay, then we'll have a point at 5, 1. We're always going to have the point at 1, 0. And then 1 over a, so 1 over 5 would have a point at negative 1. Okay, so using those 3 points, I can sketch. This is not shifted left or right, so my asymptote is not going to move. And if I plot these 3 points, 5, 1, 1, 0, and 1/5, negative 1, this is what the log curve will look like. Okay, so if we shift it, this is going to be flipped in the x-axis and then shifted up. I'm sorry, not up. Which way does that go? That should go left 3. That'll move my asymptote over here. And what else did I say? Oh, flipped. So my 3 points, we're still going to have one that's 1 unit off of the asymptote. The next one would be kind of be up 1 and out 5. Well, instead of going up, this one is flipped to be down and over 5. And then we have one that's off a 5th and up 1. So right about there, and then sketch that curve. Oh, missed my thing. Okay. Okay. Inverse of natural exponential function, so e to the x, in this case e to the y, the inverse of that is log base e. Okay, and log base e is typically written as ln. It's Latin for some version of natural log. Okay. If this is natural log of e to the, okay, or log base e of e to the, those are basically inverse functions. They're just going to cancel each other, so this would just simplify to 1/3. Okay, same kind of thing here. E to the natural log. This would just simplify to 8. Okay. Natural log of 1 or log with any base of 1 is just equal to 0, so that's just 15 times 0. And natural log of e is just 1. This is just over 6. Okay, so we are going to be solving more equations. And often it will be easier to rewrite them in the appropriate form. So like for this one, if I want to get that x out of the log, I'm going to rewrite it in exponential form. And use this loop-de-loop to make that 2 to the 3rd power is equal to 2x plus 1. 2 to the 3rd is just 8. So then we can subtract 1 and divide by 2. And that should be 7/2. Over here, this one I'm going to just use the property. Natural log of e to the x is just x. And so that'll be x equals 5. And then these two, we have an x in the exponent, so I'm going to rewrite these in logarithmic form to solve. So if the base of the exponent is e, that'll be the base of my log, so I'm going to make this natural log of something equals the exponent, is 2x plus 5, okay? So this is in log form. If I'm going to solve this, I am going to need a calculator, or we can just leave it in simplest form. So I'm going to go ahead and do it both ways. I can just subtract 5 from this, from both sides. Notice that 5 is not inside the log, so I cannot combine the 8 and the 5. And divide by 2. This is natural log of 8 minus 5 over 2. That is in simplest form. Or if we want to get a decimal, we're going to go nearest thousandth. So natural log of 8, make sure you hit enter or close your parentheses before subtracting 5. And then divide by 2. So this is approximately negative 1.460. So I'm going to do the same thing for D. I'm going to do it in simplest form first, and then then we'll find the decimal. So for this one, before I rewrite it in logarithmic form, I want to get rid of this 2. So I'm going to divide both sides by 2. We definitely cannot combine the 2 and the 10, because the 10 has an exponent that the 2 doesn't have. So those are not like things that you can combine. That's why I'm dividing it. That's just going to be 5/2. I'm going to rewrite this in log form because the base of my exponent is 10. I want the base of my log to be 10, so this will be common log of something equals the exponent. And then if I want to isolate the x, two ways we can do that. I'd probably add x and then subtract the log. Basically, those are going to get flip-flopped places. So this is equivalent to x equals 2 minus the log of 5/2. That's in simplest form. And on my calculator, 2 minus log 5/2 is approximately 1.602. I don't think I need my calculator for the next two. For e, I'm going to go ahead and divide both sides by 4. So this is log of base something of 9 is equal to, and if I divide by 4, that's just going to be 2. If I rewrite this in exponential form, this would say x squared equals 9. So, taking the square root, my x needs to be plus or minus 3. But what do we know about the base of a log? Okay, it cannot be negative. On the first page, we said that the bases have to be positive and not 1. So this cannot be negative 3. Only want the positive 3. Okay. And one more. Go ahead and solve that one and put it into your Edpuzzle because I'm running out of time. Nice.